All right, so the other thing that we will see a lot in impulse and momentum is force versus time graphs, okay? So just like before, right, if you saw a force versus delta x or distance graph, you should be thinking about energy, okay? If you see a force versus time graph, you should be thinking about momentum, all right, and impulse, okay? All right, so force times time, right, because we know that force times time equals the change in momentum. That's the area, right? If it's a box, right? Like if it was force times time, that area would be the impulse, all right? But often it might not be a constant force or any other number of things can happen, okay? But still that area is going to be the impulse, okay? So say that these are two situations with, say, like a car or a cart. I think I did something like this last year, but I couldn't find the, I don't have anything at home anyway. Okay, so if I have this car, right, traveling into a wall, let's say, okay, and then, you know, turning around and coming out, right? What would be the difference between 1 and 2? Like, what would be the difference? Let's say that it goes in at the same speed, comes out at the same speed. Okay, all right. Part 1, right? If the same momentum change is going to happen, the area has to be the same, okay? So it might be like a short, fat triangle, all right? Or it might be a tall, skinny triangle, okay? But if I want the same momentum change out, I'm going to have the same area underneath, okay? Right? So this one, 2, this is a much smaller time, so it's going to require a bigger force. Okay, so this might be like if it just banged into the wall with nothing and just banged in and came out. That's it. Okay. All right. On situation 1, right, what I'm able to do is I'm able to increase that time so the force is going to be less. Okay. So this might be some kind of like a hoop or a bumper. We have these like flexible hoop things at school, like some kind of a hoop or a bumper that sort of compresses and makes that time that it's contacting the wall longer, okay? So some kind of a squishy, bendable bumper of some sort could increase that time, which would actually lessen the force that the cart feels, but it would still get the same momentum change out, okay? So every time you see a force versus time graph, the area, okay, or in a minute when we do calculus, the integral is going to be the impulse, okay, or the change in momentum. Got a new tip, but this still is not working. My pen is like weird. Okay, all right. Okay, so here might be an example. Okay, at t equals 0 seconds, a 2.5 kilogram block, okay, is sliding at 23 meters per second, 2.5 kilogram block, over a frictionless surface to the right. Okay, all right, and let's make this positive. All right. It is then acted on a net force in the direction of motion, right? Also positive, that varies with time as shown in the graph below. Okay. What impulse does the force exert on the block during the time period shown? Okay. So whenever you see a graph and it asks for impulse, then guess what? You're looking for area. Okay. So this one is just, we don't need calculus or anything. We can just do area. So this box is 12 times 4. Okay, and this is 12 times 8, so half of it, so 6 times 8, so also 48, right? Yeah, okay. All right, so the total impulse then would be positive 96 Newton seconds, right? Force times time, okay? All right, so that's the change in momentum, okay? So for 2, what is the block's momentum after 12 seconds? Okay, so the impulse would be the change in momentum. Okay, so the final would be, oh, I don't know if I wanted to write it like this. Let me show you another way. J plus P naught. Okay, I kind of like when we're looking at the pictures, right, like we did in the lab, I kind of like, instead of writing it like this, right, it'll come out the same. I kind of like how we did with energy. So the initial plus the impulse equals the final. Okay, and then the impulse might be positive or negative. Okay. All right, but this will come out the same. Okay, so mv plus j, 2.5 times its initial was, 23 meters per second plus 96 Newton seconds, kilograms. Okay, and again, bad calculator. 2.5 times 23. Okay, so that's going to be 57.5 kilogram meter per second plus 96 Newton seconds. Okay, remember those are equivalent units. I probably need to add that up in the top part. Okay, plus 96 is 153.5 meters, kilogram meter per second. Okay, that's the final momentum. Okay, and then if I want the block's speed, let's go down here. Okay, it's just mv, right? I can just divide by m. Okay, so 153.5 divided by the original mass, which is 2.5, it's now going to be going 61.4 meters per second. Okay, and it's faster and it's still positive, which makes sense, right? Because the force is being applied in the same direction that it's moving. Okay.